This is SpaceTime, Series 20, Episode 83, coming up on SpaceTime. The mysteries of antimatter continuing to puzzle physicists. New ways to determine the size of monster black holes, and trying to determine the origins of rich organic material discovered on the dwarf planet Ceres. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
New super-precise measurements by physicists with the BASE collaboration have placed new constraints on the differences between matter and antimatter. Technically, antimatter and normal matter are the same, just that they have opposite electrical charge. So, the antimatter counterpart to the positively charged proton is the negatively charged antiproton. And the antimatter counterpart to the negatively charged electron is the positively charged positron. The thing is, equal amounts of matter and antimatter were created in the Big Bang 13.8 billion years ago. And because matter and antimatter annihilate each other as soon as they come into contact, the universe should have disappeared in a massive gamma-ray explosion almost as soon as it formed. But clearly that didn't happen. And the thing is, scientists have no idea why it didn't happen. Nor for that matter do they understand why the universe is composed almost exclusively of matter. Now, using a novel two-particle measurement method, the BASE collaboration have measured the magnetic moment of the antiproton with a precision some 350 times higher than any previous measurement. The magnetic moment is an essential component of particles which can be depicted as roughly equivalent to that of a miniature bar magnet. At its core is the question of whether the antiproton has the same magnetism as the proton. The results, published in the journal Nature, show that the magnetic moments of both the proton and the antiproton are incredibly close, meaning that so-called CPT asymmetry, a key factor in the lack of antimatter, must be incredibly small if it exists at all. CPT symmetry refers to the idea that if particles change in two of three properties, charge, parity and time, must also change in the third, and is crucial in understanding the imbalance between matter and antimatter. To perform the measurement, the BASE collaboration used a novel elegant two-particle measurement method, which was a further advance over a two-trap method previously developed. The system involves the simultaneous trapping and measurement within an even magnetic field of two separate antiprotons. The antiprotons are contained in two separate penning traps. The traps use electrical and magnetic fields to capture the antiprotons. Previous measurements were severely limited by an ultra-strong magnetic imbalance in the penning trap. In order to overcome this barrier, the authors added a second trap with a highly homogeneous magnetic field. With the experiment set up, one of the antiprotons was measured at a relatively high temperature of 350 Kelvin, a temperature equivalent to that of hot water. The other antiproton was measured at just 0.15 Kelvin, which is extremely close to absolute zero, minus 273 degrees Celsius. The antiprotons were artificially generated at CERN, the European Organisation for Nuclear Research, and they were stored in a magnetic bottle, a trap for experiments. Interestingly, the antiprotons used in the experiment were actually isolated back in 2015 and measured between August and December 2016. And that's worth mentioning because in itself that was a record-breaking achievement. It was the longest storage period ever attained for antimatter. That's because, as we mentioned earlier, antiprotons quickly annihilate as soon as they come into contact with regular matter, and that includes air. The storage was demonstrated for 405 days, the vacuum containing 10 times fewer particles than interstellar space. The first antiproton is used to calibrate the magnetic field by measuring a property known as cyclotron frequency. The second is used to measure a quality known as the Larmor frequency, which looks at the precession of the particle's spin, allowing precise measurements of the magnetic moment. Taken together, the Larmor frequency and the cyclotron frequency form what's known as the G-factor, a measurement of the strength of the magnetic field. The G-factor ascertained for the antiproton was then compared with the G-factor for the normal proton, which the BASE collaboration had already measured with the greatest known precision back in 2014. Using this new method, they found that the magnetic moment of the antiproton is 2.792847344142, measured in units of nuclear magneton, and a value extremely close to the figure of 2.7928743509, measured in 2014 by the collaboration for the proton. By improving the precision of the results by a factor of 350, It allows physicists to compare matter and antimatter with an unprecedented level of accuracy. In addition to showing that they're so close, the results also put strict limits on the possibility that a difference in the magnetic moments could be based on factors that, at the high energies which existed in the early universe, could have caused the process of spontaneous symmetry breaking, leading to differences in matter and antimatter. The authors say the results clearly confirm that CPT invariance does seem to hold at very high precision, as the magnetic moment of both the proton and antiproton still look virtually identical, apart from the signs, thus confirming the standard model of particle physics. This is SpaceTime. I'm Stuart Gary. Astronomers have discovered what could be an easy way to determine the size of the supermassive black holes found at the centres of spiral galaxies. A report in the Journal of the Monthly Notices of the Royal Astronomical Society claims there's a direct relationship between the geometry of some types of spiral galaxies and the hidden supermassive black holes at their centres. Black holes are so named because the gravitational pull on anything which falls beyond their event horizon, the point of no return, is so great that the escape velocity from a black hole exceeds 300,000 kilometres per second, the speed of light in a vacuum. And since nothing can travel faster than the speed of light, nothing, not even light, can escape a black hole. Because black holes are invisible, astronomers can only detect them by their effect on the space around them. Virtually all galaxies are thought to have supermassive black holes at their centres, each of them millions to billions of times more massive than our Sun. Traditionally, astronomers study them by measuring the speed of stars and gas orbiting around them, and from that you get a pretty good measurement of how massive the central black hole must be. Now, astronomers from Melbourne's Swinburne University and the University of Minnesota in Duluth have developed a new way for armchair astronomers, even elementary or primary school kids, to merely look at a spiral galaxy and still be able to estimate the mass of its hidden central black hole. It was Sir James Jeans and Edwin Hubble nearly a century ago who noticed how spiral galaxies with large central bulges possess tightly wound spiral arms, while spiral galaxies with small bulges tend to display wide open spiral arms. Since then, hundreds of thousands, if not millions of spiral galaxies have been classified as SA, SB, SC and SD, depending on their spiral arms. Then, about a decade ago, Professor Mark Seeger from the University of Minnesota discovered a relationship between a central black hole's mass and the tightness of the galaxy's spiral arms. Now, Dr. Benjamin Davis and Professor Alistair Graham from Swinburne University have expanded on this work. After carefully analysing a larger sample of galaxies imaged by an array of telescopes, the authors observed an unexpectedly strong relationship which predicts lower mass black holes in galaxies with open arms of the types classified as SC and SD. In fact, they found the strength of these correlations to be as good, if not better, than any other predictive method used to determine black hole mass. And given that it's the disks of galaxies that host the spiral pattern, the study highlights the poorly known connection between galaxy disks and black holes. The new procedure also allows the prediction of black hole masses in pure disk galaxies with no central stellar bulge. In fact, the authors suggest that implies that the black holes and the disks of their host galaxies must co-evolve. Davis says the discovery will also help astronomers in the ongoing hunt for the long-suspected but so far still missing population of intermediate-sized black holes, those with several hundreds to a few thousand times the mass of the Sun, and which are too big to be stellar mass black holes and far too small to be supermassive black holes.
For years now, for nearly a century, astronomers have known since the work of Sir James Jeans and Edwin Hubble that there's been this rough correlation between the types of galaxies. If you look at spiral galaxies, you see that the large bulge galaxies tend to have tightly wound spiral arms, and vice versa. The small bulges have loosely wound spiral arms. So that's always been kind of a qualitative classification of galaxies that astronomers have known about. But our research really tries to make that a quantitative relationship. So rather than just classifying galaxies as tightly wound, medium wound, loosely wound, we actually do actual geometric measurements of it and measure a quantity called the pitch angle, which basically quantifies how tightly wound a spiral is in degrees that we can measure. And then we can use that to relate that to the central massive black hole at the center, and see what the relationship is between the two and use it to predict it in unknown galaxies what that black hole might be.
Okay, so I take it you start out by looking at galaxies whose black hole mass you already are familiar with or have a pretty good handle on.
Exactly, yeah. So our current paper that was published in Monthly Notices of the Royal Astronomical Society, basically we started with a sample of 44 spiral galaxies with known black hole measurements. So they had directly independent measured black hole masses, and then we measured precise pitch angle measurements for these galaxies and then compared them to see if there was a strong correlation. And indeed, we found a good correlation between the connection between the big black holes live in tightly wound spiral arm galaxies.
And it goes further than that, doesn't it? Because you're also looking at the size of the galactic bulge and whether or not the galaxy has one in the first place. And it becomes a situation where you can pretty well make the galactic bulge appear irrelevant for determining black hole mass.
That is the helpful thing about this relationship, because up to this point, all the previous estimation techniques to find and estimate black holes were basically related to the bulge themselves, like what the size of the bulge was in terms of luminosity, total mass, or velocity of stars, and the bulge itself. But this relationship, since it's independent of the bulge, we're now comparing the disk of the galaxy where the spiral arms live. So we're comparing properties of the disk to that black hole mass. Now, as you say, we don't have to have necessarily a bulge to get accurate measurements. So there are bulgeless galaxies out there, and our technique will work in that case, whereas the other techniques wouldn't work.
I guess the Hubble tuning fork is what we're starting with. Tell me about that.
Exactly. So the Hubble tuning fork, on one side of the fork, typically the left side, you have the elliptical galaxies. So these are massive old galaxies that don't have spiral structure in them. And then as you go across the tuning fork where it branches into the fork itself, you have one branch of the fork is where the spiral galaxies are, just normal spirals without bars. So bar is the central linear feature in a spiral galaxy. And then the other fork is the barred spiral galaxy. So our relationship works fine whether you have a normal spiral or a barred spiral galaxy. The difficulty with barred spiral galaxies is there's less spiral information because you got a bar taking up the middle of the galaxy. But you can still measure the pitch angle, and the relation works fine for that. But the other relationships that I mentioned that work well for measuring properties of the bulge, those work great for elliptical galaxies, but our pitch angles won't work for elliptical galaxies, obviously, because they don't have pitch angles. But those bulge relationships don't work as well for spiral galaxies, so we think it really makes sense to use the method that is best suited for each case. You can use bulge methods if you want to work with an elliptical galaxy, or you can use our pitch angle measurement if you want to work with spiral galaxies.
And by doing this sort of work and determining the mass of the central supermassive black hole, how does that help you with your understanding of galactic evolution?
Well, I mean, there's always been this kind of chicken versus the egg question. What came first? Was it primordial black holes that kind of seeded galaxy formation around these black holes, or was it vice versa? Did you start with galaxies and then black holes slowly grew up in their centers? So by knowing what the masses of these black holes are, essentially what we're doing is we can look at different galaxies, and using our method, we can quickly estimate a pretty good estimate of the black hole mass in there, and essentially take a census of what black holes are in galaxies around the universe, and further connect these scaling relations, properties of the galaxies to properties of the black hole, and try and further elucidate this actual connection and try and answer this age-old question of black holes versus galaxies, which came first.
Do you need a star to form a black hole in the first place? Obviously, with primordial black holes, we're talking about population 3 stars, which were really big. So they've got sort of a running jump there. But do you need a star to form a singularity, a black hole in the first place?
That's a good question. I mean, it could have come out of ripples in space-time and the moments after the Big Bang. So, I mean, these are all interesting questions. But we just hope that our methods can focus on, right now we're looking at the local universe. Right now, our study all comes from local galaxies. But our method, you only really need an image to measure the pitch angle. You just need to be able to discern spiral structure to get the geometry from there. We should be able to extend our relation into the farther regions or further back in time and space where the other methods might fail because you lose the resolution. You're not able to do some of the technical measurements that you had to do previously to get black hole measurements. So that's where our method might help a bit.
One of the things you're looking at is the possibility of finding that missing population of intermediate-sized black holes, those more than 100 solar masses but less than 1 million.
Yes, exactly. So right now, it's kind of a selection effect. We find the most massive black holes because they're easier to find at this point. They live in the big elliptical galaxies. They live in the spiral galaxies, tightly wound, big bulge spiral galaxies. But it's harder to find these intermediate mass black holes. We don't really have good examples of measurement of intermediate mass black holes at this point that we can directly compare it to. So what we hope our method can predict is that the really loose spiral arm galaxies should be where these population of intermediate black holes live. And by using our relationship to predict where these low massive black holes might live and find these host galaxies, we can then do follow-up studies by looking for signatures such as X-ray emission that might reveal that, yes, indeed, this galaxy has an intermediate mass black hole.
So where are you taking this next, the hunt for medium-sized black holes?
Yeah, that'll be down the road for sure. The very next step that we're doing is we're using the exact same sample of these 44 galaxies, and now we're going to measure detailed properties of their bulges so we can get properties like the bulge masses and luminosities of the bulges, so we can have a very nice direct comparison of the predictions from our pitch angle relationship and the predictions of properties of the bulges of these galaxies. There is one interesting case I might mention, that there's this galaxy called LEDA, and so that's LEDA, then it's 87300, so 87300. It's an interesting case where it's one of the lowest measured black holes, so it's right on the cusp of intermediate mass black hole territory, and we're going to do some studies on this, measure the pitch angles of that, and that'll be kind of like our first data point, kind of dipping down into the intermediate mass black hole regime. So that should be interesting.
That's Dr. Benjamin Davis from Swinburne University. And this is Space Time. I'm Stuart Gary. A new study claims organic rich material discovered on the dwarf planet Ceres is most likely native to the tiny frozen world. The organics were detected by NASA's Dawn spacecraft and were originally thought to have been deposited there by comet or asteroid impacts. The dwarf planet Ceres is believed to have originated about 4.6 billion years ago, together with the Sun, the planets and all the other solar system bodies. Studying the organics on this 945-kilometre wide world can help explain the origin, evolution and distribution of organic species across the solar system. Ceres is the largest object in the main asteroid belt between Mars and Jupiter. It's just beyond the so-called snow line, the boundary out from the Sun beyond which ices dominate planetary formation. Ceres composition's also intriguing, characterised by clays, sodium and ammonium carbonates, all suggestive of a very complex chemical evolution. The role of organics in this evolution isn't fully understood, but scientists think it has important implications for astrobiology. One of the study's authors, Dr. Simon Markey from the Southwest Research Institute in Boulder, Colorado, says the discovery of a locally high concentration of organics close to the Imhotep crater on Ceres poses an interesting conundrum. Was it localized organic material delivered to Ceres after its formation by asteroids or comets, or was it synthesized and or concentrated at a specific location on Ceres by some sort of internal processes? The problem is both scenarios have shortfalls. So Markey and colleagues used computer simulations to try and work out what's going on. Earlier research focusing on the geology of the organic-rich region was inconclusive about its origin. So, the authors looked at the viability of organics arriving at Ceres through asteroid or comet impact. However, they found that comet-like projectiles, which have relatively high impact velocities, would lose almost all of their organics through shock compression. Impacting asteroids, which have lower incident velocities, can retain between 20 and 30% of their pre-impact organic material during delivery, especially for small impactors at really oblique impact angles. The problem is the localized spatial distribution of organics on Ceres seems difficult to reconcile with delivery from small main-belt asteroids. Marchi says the findings tend to support the idea that the organics are far more likely to be native to Ceres. This is Space Time. I'm Stuart Gary. NASA has authorized a second extension of Dawn's mission to Ceres. The Dawn spacecraft is the only mission to have orbited 2 extraterrestrial worlds. It first orbited the giant main-belt asteroid Vesta for 14 months during 2011 and 2012, before continuing on to Ceres, achieving orbit insertion in March 2015. During this extension, the spacecraft will descend to lower altitudes above Ceres' surface than ever before. Mission managers say the spacecraft will now continue orbiting Ceres for the remainder of its science investigation, and will remain in a stable orbit indefinitely after its hydrazine fuel runs out. Mission managers are now studying ways to maneuver Dawn into a new elliptical orbit, which will take the spacecraft to less than 200 kilometres above the Ceres surface. Previously, Dawn's lowest altitude, or perigee, was some 385 kilometres. A priority of the second Ceres mission extension will be collecting data using Dawn's gamma-ray and neutron spectrometer, which, as the name suggests, measures the number and energy of gamma rays and neutrons. The information is important for understanding the composition of Ceres' uppermost crustal layer and how much ice it contains. The spacecraft will also take visible light images of Ceres' surface geology with its camera, as well as measurements of Ceres' mineralogy with its visible and infrared mapping spectrometer. The extended mission also allows Dawn to be in orbit while the dwarf planet goes through perihelion, its closest orbital approach to the Sun, which will take place in April 2018. At closer proximity to the Sun, more ice on Ceres' surface may turn into water vapour, which in turn could contribute to the weak transient atmosphere detected by the European Space Agency's Herschel Space Observatory prior to Dawn's arrival. Building on Dawn's findings, the team has hypothesized that water vapour may be produced in part at least from energetic particles from the Sun interacting with ices in Dawn's shallow surface. Scientists will combine data from ground-based observatories with Dawn's observations to further study these phenomena as Ceres approaches perihelion. Mission managers estimate the spacecraft will continue operating until at least the second half of 2018. Because of NASA's commitment to protect Ceres from earthly contamination, the Dawn spacecraft won't land or crash into Ceres once the fuel runs out. Instead, it will carry on doing as much science as it can in its final planned orbit, where it will then remain until long after it can no longer communicate with the Earth. I'm Stuart Gary. This is SpaceTime. Astronauts aboard the International Space Station were twice forced to undertake emergency repairs to one of their spacesuits during a scheduled EVA last week. An EVA, or extravehicular activity, is NASA speak for spacewalk. The EVA was one of 3 scheduled over the past month to undertake routine maintenance work outside the orbiting outpost and to replace a faulty exterior camera. NASA astronaut Joe Ackerbar was just an hour into the 7-hour EVA when mission managers noticed that one of his safety tethers was frayed and damaged. Spacewalking astronauts always use 2 of these safety lines, just in case one breaks. They also wear a jetpack as an additional safety measure in case both tethers fail. This provides spacewalkers with 3 independent safety systems when performing EVAs so they can get back to the space station. Ackerbar had to stop work, hold on and wait, while fellow spacewalker NASA astronaut Randy Bresnik went back to the space station's airlock, grabbed a spare tether line and attached it to Ackerbar's spacesuit. NASA stresses that Ackerbar was never in any real danger, as he was always securely attached to the space station by the second tether. However, just 4 hours later, mission managers noted that the right handle on Ackerbar's emergency jetpack had somehow popped open. Bresnik was again called on to assist getting some tape and securing the wayward handle back down. By this time, mission managers decided the jetpack should be deemed unreliable until it's inspected, and they ordered the EVA to be aborted as soon as the spacewalkers had finished their current job, which at that point was greasing a new robotic arm. The astronauts then returned to the safety of the space station. The spacewalk was the 205th EVA undertaken from the space station. You're listening to SpaceTime. I'm Stuart Gary. A new classified spy satellite has been blasted into space for America's highly secretive National Reconnaissance Office. The NROL-52 mission was launched on an Atlas V rocket from Pad 41 at the Cape Canaveral Air Force Base in Florida. The 58-metre tall Atlas V uses a Russian-built RD-180 motor burning RP-1 kerosene and liquid oxygen for about 4 minutes. In its 4-2-1 configuration, the Atlas V is also fitted with 2 strap-on Aerojet solid rocket boosters. The Atlas V Centaur upper stage is powered by an Aerojet Rocketdyne RL-10C1 engine burning liquid hydrogen and liquid oxygen.
Status check.
Go Atlas. Go Centaur.
Go NROL 52.
20, T-minus 10,
9, 8, 7, 6, 5, 4, 3, 2, have ignition, and liftoff. Liftoff of the United Launch Alliance Atlas V rocket carrying the NROL 52 mission for the National Reconnaissance Office.
Booster has gone to closed loop PU control. Pitch program's complete. SRB chamber pressures are relative as expected. And booster has throttled down right outside launch response is good. Mach 1 and booster's throttled back up. Max Q. Ready 180 chamber pressures. Good. SRB chamber pressures have plateaued. Booster engines all continue to look very good. Body rates controlling down the middle. And up on SRB burnout momentarily. And we have indication of SRB burnout. Signatures look good. We have throttled back up to 100% thrust. Engine response is good. RD-180 continues to look very good at this point, as the booster is now 50%. Its liftoff weight. Current altitude is 25 miles. Downrange distance 27 miles. Current velocity 3,543 miles per hour. And we have indication of 2 good SRB jettisons. And we have begun flying the Q Alpha limited steering portion of flight. Booster has throttled down right on schedule. RCS pyro valve has been fired. That system is now pressurizing to flight levels. Signatures look good. Current altitude is 42 miles. Downrange distance 85 miles. Current velocity 6,155 miles per hour. Range track is good. Body rates are as well. Booster is now 1/4 its liftoff weight. Coming up on our 5G throttle segment. Boost phase cooldown has begun. Signatures look good. We have fired the pogo bleed. Now throttling to 4.6 Gs in preparation for BECO. Boost phase cooldown is complete. And we have BECO. Engine shutdown looks good. And we have indication of stage separation. We have LOX and fuel pre-start on the RL-10. GN2 purge firing is underway for the RCS. We have ignition and full thrust on the RL-10. And we have indication of payload fairing jettison. Looks like a clean set. Centaur steering has been enabled.
This is Atlas Mission Control at T plus 5 minutes and 2 seconds. An Atlas V rocket carrying NROL 52 for the National Reconnaissance Office lifted off at 3:28 a.m. Eastern Time, and all systems continue to operate as expected. At our customer's request, we will now conclude this morning's live mission coverage.
The mission is highly classified. And so, as is customary on SpaceTime, we'll fill you in on all the details regarding the payload. Well, this top-secret payload is thought to be a new 4th-generation SDS, or Space Data Systems Communications Relay Satellite. These spacecraft are designed to relay intelligence collected by other spy satellites, including Keyhole Imaging Reconnaissance Satellites and La Crosse Onyx Radar Reconnaissance Satellites, as well as providing communications links for the U.S. Air Force Satellite Control Network and for U.S. military aircraft flying at high latitudes. While some SDS satellites are in geostationary orbit, others are positioned in highly elliptical orbits going from perigees of just 300 kilometres out to apogees of over 39,000 kilometres. The high apogees allow them to communicate with polar stations that can't be reached by conventional geosynchronous satellites. The mission was United Launch Alliance's 7th flight this year, and the 122nd successful launch since the joint Boeing-Lockheed Martin company was formed in December 2006. The United Launch Alliance's next flight will be the Joint Polar Satellite System 1, which is being launched for NASA and NOAA, the National Oceanographic and Atmospheric Administration. The mission is slated to fly on November 10 from Space Launch Complex 2 at the Vandenberg Air Force Base in California. This is SpaceTime. I'm Stuart Gary. A SpaceX Falcon 9 rocket has successfully placed the EchoStar 105 SES-11 telecommunications satellite into orbit. The mission was launched from NASA's Kennedy Space Center Pad 39A at the Cape Canaveral Air Force Base in Florida.
10, 9,
8, 7, 6, 5, 4, 3, 2, 1, 0.
Stage 1 prop looks good.
Power telemetry nominal.
The Falcon 9 rocket as it ascends through the atmosphere carrying the EchoStar 105 SES-11 payload to geostationary transfer orbit after a successful liftoff from Kennedy Space Center in Florida.
Vehicle supersonic.
In about 10 seconds, the rocket is going to be passing through the period of maximum aerodynamic pressure. That is called max Q. Those 9 Merlin engines currently produce the thrust of 5 747s at full thrust. That's how much power the Falcon 9 is producing right now.
And back engine shell started.
In about 30 seconds, those 9 Merlin engines are going to shut off in an event called MECO, which stands for main engine cutoff. Once MECO happens, there'll be 2 other very quick succession stages happening after that. The first is going to be the stage separation, where the first stage separates from the second stage and comes back towards the drone ship. And then after that, second engine start 1, which is when the Merlin vacuum engine on the second stage ignites to carry the payload the rest of the way to orbit.
We have MECO.
Stage separation first.
And back ignition.
You can hear the applause from Mission Control. It looks like that we had a successful MECO, main engine cutoff, successful stage separation, and a successful start of the Merlin vacuum engine on the second stage.
Following stage separation, the Falcon 9's first stage successfully returned to Earth, landing on the SpaceX drone ship Of Course I Still Love You, stationed downrange in the North Atlantic Ocean.
The first stage of the Falcon 9 rocket currently expanding its grid fins, getting ready for descent back down through the engine nozzle of the Merlin vacuum engine on the second stage. In about 10 seconds, we're going to see the fairing, which is protecting the EchoStar 105 SES-11 payload, deploy from that. Successful deployment of the fairing. Fairing is only needed while in the dense region of the atmosphere to protect it from aerodynamic loads. Now that we're out of the atmosphere, we can jettison it.
Acquisition of signal Bermuda.
Cold gas thrusters, those help orient the first stage of the rocket so that it's pointed in the right direction as it comes back down through the atmosphere. So that first stage is currently pretty high up in the atmosphere. It's still, the gas of the atmosphere is still very thin up there. So as it approaches the much thicker parts of the atmosphere lower down, it's going to execute an entry burn in about a minute and a half. This entry burn is going to slow the rocket down so that as it hits the thicker parts of the atmosphere, it doesn't experience any excessive heating from compression of the atmosphere. When on the launch pad, the weight of the Falcon 9 rocket is actually about 90% fuel. So right now that first stage is mostly empty, having expended most of its fuel to get the second stage up to orbit. That first stage, therefore, because it's so light, doesn't really need that much thrust to slow down. Those Falcon 9 Merlin engines actually operate at full thrust regardless of how much fuel is in the rocket. And so the entry burn is only about 20 seconds long. Currently, we're getting good telemetry back from the first stage and the second stage. Trajectory is good for both, and the engine chamber on the Merlin vacuum engine is holding steady. We should be seeing the entry burn of that Falcon 9 first stage in just about 10 seconds.
Stage 1 AFTS has saved.
And there's that entry burn beginning.
Stage 1 entry burn is started.
Still getting good telemetry from the second stage as it continues to climb, carrying that EchoStar 105 SES-11 payload to its intended geostationary transfer orbit. We had a good entry burn, and the first stage is still on track to touch down on the deck of Course I Still Love You in the Atlantic Ocean.
Drone ship AOS.
And that first stage is scheduled to start its landing burn in just about
Stage
30
1 is
seconds.
transfer.
Currently, the second stage is still burning happily. We have good telemetry from the second stage, still on course for a geostationary transfer orbit.
Stage 1 landing burn is started.
Stage 2 AFTS has saved.
The drone ship, Of Course I Still Love You.
Legs have deployed.
Good to see you. Falcon 9 rocket is currently standing on the deck of Course I Still Love You. Yet another successful landing of the Falcon 9 first stage. This is our 18th successful landing of the Falcon 9 rocket.
It's the same Falcon 9 first stage, which was previously used back in February to fly the Dragon Ceres 10 cargo ship to the International Space Station. Built by Airbus Space and Defence, the 5,200 kilogram EchoStar 105 SES-11 uses a Eurostar 3000 platform equipped with 24 Ku band and 24 C band transponders. The satellite will be positioned in geostationary orbit with a footprint covering the Americas, including Alaska and Hawaii, as well as Mexico and the Caribbean. The flight came just 3 days after the company's previous launch, flying 10 Iridium NEXT satellites from the Vandenberg Air Force Base in California. It was also a record-setting 15th SpaceX Falcon 9 launch this year. And it's not over yet. The next SpaceX Falcon 9 launch will be the KoreaSat 5A telecommunications satellite, also slated to fly from Pad 39A at the Kennedy Space Center on October 30. I'm Stuart Gary. You're listening to SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. As debate over marriage equality continues across Australia in the closing days of the plebiscite, the Christian lobby is accelerating its efforts to focus attention away from the human rights aspect of the issue and onto the potential impact on children being brought up by same-sex parents. Under Australian law, same-sex couples can already adopt children. So children are already being raised by same-sex couples. And according to the Christian lobby's claims, children and adolescents with same-sex parents are at risk of poorer health and well-being than other children. The claim has, however, been strongly rejected by doctors, and now 13 of Australia's leading paediatricians have published a review in the Medical Journal of Australia looking at all the available evidence, finding that children raised in same-sex parented families do every bit as well as children raised by heterosexual partners. The findings also reflect the conclusions reached last month by Australian skeptics, which also looked at the available scientific evidence. However, the authors of the new study do caution that the same-sex marriage debate is raising the risk of mental health problems for same-sex couples, their children, and young people who identify as LGBTIQ. A new study warns pollution has now been linked to 1 in every 6 deaths worldwide. The findings, reported by the Lancet Commission on Pollution and Health, indicates that pollution is now linked to an estimated 9 million deaths each year worldwide. Researchers found that as of 2015, a quarter of all deaths in India were related to pollution, compared to just 6% in Australia and an even lower 5% in New Zealand. The study confirms that pollution is the largest environmental cause of disease and premature death in the world today. In fact, diseases caused by pollution were responsible for an estimated 9 million premature deaths in 2015. That's 16% of all deaths worldwide, 3 times more than all the deaths from AIDS, tuberculosis and malaria combined, and 15 times more than from all wars and other forms of violence. The study concludes that in the most severely affected countries, pollution-related disease is now responsible for more than 1 death in 4. Back in 2006, boiling mud, water, rocks and gas began erupting from numerous vents in the Lusi mud volcano in central Java in Indonesia. By September of that year, the largest eruption site reached a peak, with enough mud being gushed to the surface to fill 72 Olympic-sized swimming pools every day. The relentless sea of mud has buried numerous villages, some up to 40 metres deep, and it's forced the evacuation of over 60,000 people from their homes in what's now become the most destructive ongoing mud eruption in recorded history. 11 years on, it's still going, and scientists now think they know why. Reporting in the Journal of Geophysical Research, scientists have found that Lusi is connected to a nearby volcanic system by a tunnel alongside a fault. Geologists think an earthquake caused the magma from the nearby volcano to enter the Lusi system, triggering the mud eruption. Scientists have discovered that the scorching magma from the volcano has essentially been baking the organic-rich sediments underneath Lusi. This process builds pressure by generating gas that becomes trapped below the surface. In Lusi's case, the pressure kept growing until an earthquake triggered the eruption. By studying the connection between these two systems, scientists can learn more about how volcanic systems evolve, whether they erupt magma, mud, or hydrothermal fluids. A remarkable new fossilized skeleton of a tyrannosaur dinosaur, discovered in southern Utah, has now been airlifted by chopper from the remote field site and delivered to the Natural History Museum of Utah, where it will be uncovered, prepared and studied. The fossil is approximately 76 million years old and is most likely of the species Teratophonius cori, one of Utah's ferocious tyrannosaurs that walked western North America between 66 and 90 million years ago during the late Cretaceous. At least 75% of the dinosaur's bones are preserved, including a nearly complete skull. That makes it the most complete skeleton of a tyrannosaur ever discovered in the southwestern United States. The tyrannosaur fossil is thought to be a sub-adult individual between 12 and 15 years old, about 7 metres or 20 feet long, and with a relatively short head, unlike the typical longer snouted look of northern tyrannosaurs. The new find will allow paleontologists to learn more about the southern tyrannosaur's anatomy, biology and evolution. Scientists hypothesized that this tyrannosaur was buried either in a river channel or by a flooding event, keeping the skeleton intact. The site's a complex mix of topography ranging from high desert to badlands, and most of the surface area is exposed rock, making it rich ground for new discoveries, not just dinosaurs, but also crocodiles, turtles, mammals, amphibians, fish, invertebrates, and plant fossils. And finally for now, privacy concerns have long swirled around how much information online advertising networks collect about people's browsing, buying and social media habits, typically to try and sell you something. But could someone else use mobile advertising to learn where you go for coffee? Could a burglar establish a sham company sending ads to your phone to learn when you leave the house? Could a suspicious employer see if you're using shopping ads during work time? Or could some creepy dude or dudette just be spying on you? Now research by the University of Washington says the answer is yes, at least in theory. The study suggests that for roughly $1,000, someone with devious intent can purchase and target online advertising in ways that allows them to track the location of other individuals and learn what apps they're using. In fact, researchers found that it'd be fairly easy for anyone, be they a foreign intelligence agent or a jealous spouse, to simply sign up with a large internet advertising company and on a fairly modest budget, use these systems to track an individual's behaviour. The researchers discovered that an individual ad purchaser can see when a person visits a predetermined sensitive location, a suspected rendezvous spot for an affair, the office of a company that a venture capitalist might be interested in, or in a local hospital where someone might be receiving treatment. And they can find this information out within 10 minutes of the person's arrival. They're also able to track a person's movements across a city during, say, the morning commute by simply serving location-based ads to a target's phone. The team also discovered that individuals who purchase the ads could see what types of apps their targets are using. That could potentially divulge information about a person's interests, dating habits, religious affiliations, sexual orientation, health conditions, political leanings, and other potentially sensitive or private information. Someone who wants to surveil a person's movements first needs to learn the mobile advertising ID of the target cell phone. These unique identifiers that help marketers serve ads tailored to a person's interests are sent to the advertiser whenever a person clicks on a mobile ad. A person's mobile advertising ID can also be obtained by eavesdropping on an unsecured wireless network the person's using, or by gaining temporary access to his or her Wi-Fi router. Importantly, the target doesn't need to click on or engage with the ad. In fact, the purchaser can simply see where the ad's being served and use that information to track the target through location. In the team's experiments, they were able to pinpoint the person's location to within about 8 meters. Now, technically, an individual could potentially disrupt the simple types of location-based attacks by frequently resetting the mobile advertising ID on their phones, a feature that many smartphones now offer. Disabling location tracking within individual app settings could help, but advertisers may still be capable of harvesting location data in other ways. It seems as long as you have a cell phone, the concept of retaining some sort of privacy is long gone. You're listening to SpaceTime, I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Audio Boom, YouTube, from spacetimewithstuartgary.com, or from your favourite podcast download provider. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.